The word thermodynamics comes from two Greek words, therme meaning heat and dynamis meaning power. Heat power is a pretty great name for the area of physics that gave us the steam engine. But in this video, we're looking at the flip side, cold power. This is laser cooling, in which gases are cooled to super low temperatures by high energy lasers. But before we can understand how it works and discuss some of the cool things you can do with it, we first need to talk through electron energy shells. Danish physicist Niels Bohr gained his fame in 1913 when he proposed a new model of the atom. In Bohr's atom, there's a central, dense nucleus made up of protons and neutrons, and it's orbited by electrons in discrete energy shells. Discrete is defined as meaning individually separate and distinct, a perfect description of Bohr's electron shells. One analogy I like to use when talking about discrete energy shells is to think about a staircase. As you walk up a staircase, you can put your feet on one step or another, but never halfway between two stairs. The same is true for electrons. They can only exist in discrete energy levels. You could find them in shell 1, that's the shell closest to the nucleus by convention, or in shell 2 or in shell 3, but you'd never find an electron in shell 1.5. That's meaningless. Electrons are negatively charged, and the nucleus is positively charged, and it's the electrostatic force of attraction between these two that keeps the electron in orbit around the nucleus. Because they're attracted to the nucleus, electrons all want to orbit in the lowest possible shell, where they have the least potential energy. A physicist might say the first energy eigenstate corresponds to the n equals 1 shell. We're treading now on some pretty treacherous ground, so let's make a clarification. Eigenstates in quantum mechanics are solutions to the Schrödinger equation. Let's not get bogged down in quantum mechanics. So to summarise, we know today that Bohr's model of the atom isn't quite right. Electrons are not like miniature planets orbiting the nucleus. Instead, they form a cloud of probability around the nucleus, describing where you're most likely to find them, although none of them have fixed positions. Schrödinger's equation gives us a method of determining the most likely positions for an electron within the quantum probability cloud. These positions are called eigenstates. Eigenstates, just like Bohr's electron shells, are discrete, and it's this quantized nature that allows laser cooling to take place. In the rest of the video, I'll use Bohr's model for simplicity, but the principles of laser cooling apply to the full quantum picture just as easily. Although the energy shells, or eigenstates, are discrete, electrons can still move between them when they gain or lose energy. The primary way they do this is by absorbing or emitting electromagnetic radiation. When an electron orbiting the atom absorbs an instant photon, excitation occurs, and depending on the frequency of the light, for E equals hf tells us that the energy of the light depends only on its frequency, the electron can move to a higher shell. This is where the quantized nature of shells becomes important. Only electrons that absorb exactly the right amount of energy can move into a new shell. The further the shell is from the nucleus, the larger the energy required to orbit there, because the electron has to overcome the electrostatic attraction between it and the nucleus. As mentioned earlier, electrons all want to orbit in the first shell, where their energy is lowest. And just as they can move to higher shells, electrons can also de-excite by emitting photons, and so return to lower energy shells. As a science, physics builds itself upon a set of unalterable laws, one of which is the conservation of momentum, which states that the total momentum of a closed system before an impact or an explosion must equal the total momentum of a closed system after the impact or explosion. Imagine firing peas at a beach ball. When they stick to the beach ball, the ball rolls forward to conserve momentum. If the ball then shot the peas back, it moves even faster, just like a rocket ejecting fuel. Electrons and photons follow exactly the same rule. When an electron absorbs a photon, it gets a small push in the photon's direction. Remember, relativity tells us that although photons don't have mass, they do have momentum. The electron briefly excites, then emits a secondary photon, or several photons, giving it a second push. But it does this in a random direction. There are three possibilities for this secondary photon emission. If the atom fires the secondary photon back in the same direction as the original photon came from, it essentially cancels out the push given to it by the original photon, because the two photons always have identical momentums. So the final velocity of the atom after this process is unchanged. If the secondary photon is emitted in the opposite direction to the original photon, it gives the atom a second push in the same direction, and so the overall change in velocity is 2 photons worth of push in the direction of the original photon. Those are the two extreme cases, so if the photon is emitted in one of the intermediate angles between the two, the overall change in velocity must be between 0 and 2 photons worth of push in the direction of the exciting photon. This is an extremely exciting result. When an electron is excited by a photon, no matter which direction the electron then re-emits a photon in, it will always be moved between 0 and 2 photons worth of push in the direction of the original exciting photon. At this point, you might be wondering if the video has the wrong title, because we haven't spoken at all yet about laser cooling, but the link is clear. Temperature is a measure of how much the average particle in an object vibrates. To cool a particle down, you need to minimise the amount of movement it has, and focusing lasers on atoms gives us a reliable method of moving them around. Laser stands for light amplification by stimulated emission of radiation. But really, it's just a tightly focused stream of photons. And as we've just discussed, those photons can actually nudge atoms, since every time an electron absorbs the light, it has to follow the rules of the conservation of momentum. But surely, by moving the atom around, you increase its temperature. Correct, if you kept moving it in one direction. The really clever trick is what happens when you keep moving it in different directions. Cloud Cohen-Tanoiji, Stephen Shu and William Daniel Phillips were awarded the 1997 Nobel Physics Prize for first performing laser cooling, and their method is as follows. Take the sample of gas that you want to supercool and seal it in a cube vacuum chamber. On each face of the cube, set up a laser that fires into the centre. This is done so that each axis in three-dimensional space has 2 lasers, one acting in either direction, firing through it. As the 6 incident beams of light shine through the gas, any given particle found inside the cloud is more likely to interact with a photon that is travelling in the opposite direction to its own motion. This is because of the Doppler effect. The Doppler effect is a phenomenon that explains why waves appear to change when their source is moving. Take the sound of an F1 car as it drives past a stationary observer. The noise of its engine drops from a high pitch to a low one as it speeds by. This happens because as it moves forward, any sound waves being emitted by the car in the direction of travel move slower relative to the car than those being emitted against the direction of travel. The car is chasing the sound waves ahead of it while leaving the ones behind it spread further apart. So even though the car emits sound at a constant frequency, the wavelengths appear shorter in front and longer behind. Thanks to relativity, only the stationary observer notices this distortion. To the driver moving with the source, the sound waves seem perfectly normal. That change in wavelength explains the familiar rise and fall in pitch as the car passes. The faster it moves, the greater the difference. And if the car could break the speed of sound, about 330 meters per second, it would overtake its own sound waves, creating the sharp crack of a sonic boom. The Doppler effect applies to all types of waves, including light waves. In laser cooling, the 6 beams of light fired into the gas cloud have a very specific frequency, which is slightly below the required frequency needed to excite an electron. The atoms in the gas cloud are constantly in motion, all in random directions relative to one another. Particles that move in the same direction as a laser beam perceive that light to be redshifted. This is because the light's wavelength has increased due to the Doppler effect, and so is closer to the red end of the spectrum. Because the wavelength of the light increases, the frequency of the light must also decrease because V is equal to F lambda. Therefore, particles moving in the same direction as the incident light do not absorb it, as the frequency of the light is too low to cause electron excitement. The opposite is true for particles that move against the incident light. These particles perceive the beams of light to be blue shifted, the wavelength is shorter, and the frequency is higher. To a stationary electron, the frequency of the light is slightly below what's required to excite electrons. So when the light's frequency is increased by the Doppler effect, the atoms moving in the opposite direction can absorb the photons as the frequency matches the required energy to move to a higher shell. To conclude, an electron will only absorb a photon from one of the 6 lasers if the atom it's orbiting is moving in the opposite direction to the laser. As the lasers act in 3 dimensions, no matter which direction the atom's moving in, it will always be moving opposite to one of the lasers. How does this help cool down the atom though? Picture the movement of one gas atom in the chamber. For now, let's imagine it's moving in one dimension, it's moving along a line. Based on its initial direction, it will absorb a photon from whichever laser is firing most opposite to its direction. We'll call this laser laser A. When it absorbs the photon from laser A, it will be pushed anywhere from 0 to 2 photons worth of push towards laser B on the other side of the chamber. When this push happens, it causes the atom to slow down relative to A. Laser A emits a huge number of photons, and the atom continues to absorb them and continues to slow down until it's so slow that the Doppler effect no longer blue shifts the photons enough for them to be absorbed. At this turning point, the force of a 2-photon push is enough to actually reverse the direction and accelerate the atom towards laser B. When this happens, the photons coming from laser B are now blue shifted, and so the process repeats itself until eventually the atom reaches an equilibrium. The atom absorbs 1 photon from A and accelerates towards B. Then it absorbs 1 photon from B and accelerates towards A. In 3D, this works exactly the same. The atom is also caught in equilibrium between lasers C and D and E and F. Because the rate of photons escaping the 6 lasers is exceptionally high, the atom doesn't accelerate in any one direction for very long. In other words, it hardly moves at all. And hardly moving is the very definition of low temperature. The best laser coolers use lasers that emit as many photons as possible, all with frequencies as close as possible to the stationary excitation frequency. These can cool atoms down to millikelvin, millionths of a degree above absolute zero, the coldest possible temperature. At absolute zero, the only motion that the atom undergoes comes from its quantum zero-point energy. That's definitely cool, but it gets cooler when you explore the things that laser cooling can achieve, one of which is creating Bose-Einstein condensates, which are named after its joint discoverers, Indian physicists Sachinderya Nath Bose and Albert Einstein. Bose-Einstein condensates occur when small groups of particles, only about 1 million atoms, are bound together at very, very low temperatures after laser cooling. When in this state, which they usually only occupy for a few milliseconds, they exhibit the quantum behaviour of one particle. This means they show some incredibly interesting properties, like having a macroscopic wave function, acting as a superfluid, and creating anomalous magnetic responses. But these exciting quantum properties will have to wait for another video. And to make sure you don't miss out on that one, consider subscribing. Thank you.